Hello everyone, I'm Zaira Pindado. I'm going to present somewhere statistically binding commitments, which is a joint work with Prastudy, Fauzi, Helger, Lipmaa, and Janno, Siim. We present a new primitive, which is a generalization of dual mode commitments already used in the literature as a building block of commit and proof constructions for NP languages. A commitment scheme is one of the most important primitives in cryptography. Briefly, a commitment scheme is a protocol where a party commits itself to some secret value that can be revealed after some time. This value can be the solution of a problem or a vote. We can think about it as an envelope, where the value is not revealed until the party who committed decides to open it. There are two classical requirements, hiding and binding. Hiding ensures secrecy. Who has access to this commitment cannot gain any knowledge about the secret value. Binding provides an ambiguity. In the revealing phase, the value that is revealed corresponds to the value used to the committed phase. Different security notions are used for these requirements, like perfectly, statistically, and computationally. It is well known that we cannot have perfectly hiding and perfectly binding at the same time. We can have perfectly hiding and computationally binding, and vice versa. We are interested in these primitives because commitment schemes appear naturally with non-interactive zero-knowledge proofs for NP languages. Imagine that we want to prove that there exist some variables that satisfy a set of quadratic equations. If we use the commit and prove strategy, we will commit to our solution and we prove that they satisfy the equations. If we generate the parameters with a trapdoor that can be an extraction key, in the soundness of the non-interactive zero-knowledge proof, we can open the commitment using this trapdoor to extract the solution, and then use it to derive a contradiction between the solution and the proof and break a hard problem, and so conclude the soundness proof. This is applied in snarks, for example, for digital transactions. Snarks are the most efficient non-interactive zero-knowledge proof for general languages, and they are used to prove correctness of computation and that the party has enough amount of money, committing to the money that is never revealed. Technically, in a snark, we commit to the witness and we prove the satisfiability of the gate of the circuit, and we use some knowledge assumption, which is non-falsifiable and kind of artificial, which provides that we can extract completely the witness and use it to break the hard problem. We want to note that in that case, we have a succinct commit and succinct proof. And the knowledge assumption allows us to extract beyond the information theoretical bound, because we can extract the whole witness and then use it to break the hard problem. So one question is, what is the best in efficiency terms that can we do to prove soundness for an NP language under falsifiable assumptions? Because by Gentry and Quick's impossibility result, we know that this cannot be succinct. So what is the best that we can do? Several works have given constructions with a linear commitment and a constant proof. Linear in the witness size or in the depth of the circuit. We want to focus in this result that is a quasi-adaptive non-interactive argument for bit strings. This construction of González, Debian, Raffles for proving a commitment vector opens to bits. The authors provide commitments to each element, so this is a linear commitment, and a proof for satisfiability of these equations that are equivalent to that these elements are bits. This construction is quasi-adaptive, which means that the CRS is dependent on the relation, concretely on the equations. And this provides to can have an aggregation technique and have a constant size argument under falsifiable assumptions using the following strategy. What they do is they give an additional commitment to the same vector and a proof for both commitment open to the same value and another proof that this commitment opens to an element from the set that we want. These proofs are constant and they present a new commitment that is an extended Multi-Pedersen commitment, which is very similar to Multi-Pedersen commitment, but in that case they extend to have one index that is statistically binding and statistically hiding at all other indexes. In this commitment, only who computes the commitment key knows this index where the commitment is statistically binding. And then who has access to the extraction key is able to extract the component in this index. And this is used to the soundness proof. How? Strategy is to guess an index J where the prover cheated, and then change to again where the extended Multi-Pedersen commitment is statistically binding at this component. So we can extract this Vj corresponding to an element that is not a bit and use it to break the computational falsifiable assumption. So in these constructions of commit and proof for NP languages under falsifiable assumptions, the best that we can hope is to have constant proof and a linear commitment. The challenge that we have to face in that cases is to construct a security proof that breaks a hard problem by combining constant size information of the witness that we obtain from the proof part and the whole witness that we obtain from the commitment part. González, Levy, and Raffles solve it by this strategy of extracting from just one coordinate of the shrinking commitment. What we do is to define somewhere statistically binding commitment scheme, which is a generalization that allows extraction of a set of coordinates, which provides additional flexibility that can be useful to apply this strategy to other contexts. So we define somewhere statistically binding commitments that are non-interactive and they are defined in the CRS model. The parameters are n, that is the length of the vector that we are committing. S is a set of indices of size at most q of integers between 1 and n that is chosen in the commitment key generation. And we have these properties. Indexed hiding means the commitment key reveals nothing about the indexed S. Somewhere statistically binding that the commitment to the vector is statistically binding at the values corresponding to the indexes in S and statistically hiding in the other indices. So we say almost everywhere statistically hiding. And finally, we have F extraction. We call somewhere statistically F extractability, with this F being some function, for example, the exponentiation in the group. So given a commitment to a vector and the extraction key, one can extract the values F of the vector at those indexes of S. In this paper, we formally define the somewhere statistically binding commitment schemes, and we prove that they are the that they achieve the classical notions of commitment schemes. We show that extended multi-Pedersen commitments are a special case of our commitments. We also give a characterization of algebraic commitment schemes that are when the commitment key is a matrix function, and how we can express all the somewhere statistically binding properties in terms of membership in linear spaces. We also give a definition of a new primitive that we call functional somewhere statistically binding commitment scheme, that is a generalization where we commit to the functions of the vector that we are committing instead to the vector itself. And we give some applications of these functional somewhere statistically binding commitments. One of our results is to prove that these SSB commitment schemes are actually commitment schemes in the classical sense, with computationally binding and computationally hiding properties in all the coordinates. So we do it using this theorem. In the first case, we prove that if we have indexed hiding and somewhere statistically binding, then we have computationally binding. We do it by assuming that some adversary can break computationally binding with non-negligible probability, and then we construct this algorithm B who switches the commitment key to another one with the same parameter NQ but different set. We have that both games are indistinguishable by the indexed hiding property. And so we can use the output of A that are two vectors that are different but with the same commitment. Because we have a lemma where we prove that with non-negligible probability, these two vectors at the coordinates of the index set S prime are different. So we have that, and we have the commitment is the same, so B can break the SSB property with non-negligible probability. Very similarly, we prove the second result where we have indexed hiding and almost everywhere statistically hiding to prove that we have computationally hiding everywhere. One of our constructions is the extended multi-Pedersen commitment, where we define this matrix distribution, which is clearer in the example. So we start, if we have n equal to 3, we start extending with one extra index, and we construct a matrix that has n plus 1 columns. We initiate this putting zeros everywhere and a 1 in the last column in the last position. So we have this column, and we are going to construct columns that are linear dependent to this one if the index corresponds to the indexes outside of S, and linear independent if the indexes correspond to S. By this, if we multiply this matrix M by a vector, we keep the information of the vector in the positions corresponding to the statistically binding. So, and we also sample this R, that is a randomizer matrix, and we use it to construct the commitment key, that is this R times M in the group. So to commit a vector X, we multiply this commitment key by X. By doing so, if anyone has access to this R, that is the extraction key in the field, it can efficiently compute R minus 1, the inverse of R, and multiplying that by the commitment, then it will obtain this M times X in the group. So from this, you can extract the components of X corresponding to the indices of S. That is where we have the information of X multiplied by 1, but everything in the exponent. For different sets S, we have the matrix distributions are indistinguishable under the matrix decisional Diffie-Hellman assumption. We also define this generalization, which is functional somewhere statistically binding commitments that are commitments to functions f corresponding to some family of functions of the committed vector. In that case, we have function set hiding instead of index set hiding. The commitment key hides the functions in that case. And the extraction in that case corresponds to f extracting the functions of the vector that we committed. In the case that the family is for linear functions, we have the linear extended Multi-Pedersen commitment that it was already used in Daza et al. Construction for Boolean circuit satisfiability, where they have linear size commitment of the witness and a shrinking commitment of the witness that is used in a very similar way as González, Debian, Raffles that we already saw, where they change the commitment key of the shrinking commitment to be statistically binding at 3 indices and make the adversary compute 3 linear functions of the witness. They can extract these 3 linear functions in the group from this shrinking commitment and use them to break the hard problem. So we generalize this idea by giving this linear EMP commitment that allows to extract Q linear functions. We give the formal definition and we represent the function by a matrix that is given in the group. And interestingly, we show that the security properties and results that hold for somewhere statistically binding commitment also hold for the functional version of them. We present different applications. First of all, we construct a quasi-adaptive, non-interactive zero-knowledge argument for arithmetic circuit satisfiability with a very similar strategy to Daza et al. We adapt their soundness and their construction to a square arithmetic program, which is a language for arithmetic circuits of Roth and Muller, instead of a square span program that it was for Boolean circuit case. And we use our linear extended Multi-Pedersen commitment as a black box. Since we formally defined and proved F extraction, we can use these linear EMP commitments as black box and have more compact and clear representation. We have 2 applications in Oblivious data queries. The first, Oblivious database queries, we have a sender who has access to some database and a receiver who has some functions, and it was the functions evaluated in this database. So the receiver computes some commitment key that depends on this matrix and sent to the sender. The sender computes the commitment using this commitment key and its database and sends it to the receiver. So the receiver can extract the evaluation of its functions in the database from this commitment without revealing the functions. The privacy of the receiver is guaranteed by the function set hiding property, and the privacy of the sender is guaranteed by the almost everywhere statistically hiding. We have also Oblivious linear function evaluation, which is another application very similar, where in this case the sender has the functions and the receiver has the database. Thank you for hearing me.